In this video, we will discuss the analogues of the finite's theorem for two-dimensional arrays, given by the so-called Aldous-Hoover representations. Okay, so we will consider an array S indexed by two indices now, L and L prime. And it will be again an infinite dimensional array. And let's begin with the first definition. Namely, we say that this array is exchangeable if the following holds. Namely, if we permute the indices of this array by some one-to-one functions pi and rho, then we get the array with the same distribution. For any one-to-one functions pi and rho. So in other words, again, since this is really a statement about finite dimensional distributions, if you take any number of rows and any number of columns, then the distribution of that block will be the same no matter where that block is located. One simple example of such an array is the following. Now, if we take the elements of this array to be the following function of independent uniform random variables, okay, where all these arguments are IID uniform on 0, 1. Okay, and this function sigma is, of course, a measurable function of these four arguments taking values classically in the real line. Of course, later we will allow the elements of this array to take values in general Borel spaces or complete separable metric spaces. And we can see here that such an array is clearly exchangeable because permuting the rows and columns here just corresponds to relabeling these IID uniform random variables. Permuting the rows just corresponds to relabeling these ULs, and permuting columns corresponds to relabeling VLs, and any permutation of rows and columns just reorders these X's, but these X's can be reordered in any way you like. They are IID for all indices in our array. Okay, but it turns out that this simple example of an exchangeable two-dimensional array actually covers all the possibilities. And this is a theorem which is called Aldous-Hoover representation. Okay, and it will be part 1. We'll give another version of this theorem in a second. So it says that all exchangeable arrays are of this form in distribution. Okay, in other words, there exists a choice of this function sigma so that the array will be equal in distribution to array of this form. There is also an analog of this result for any dimensional array, but here we will just focus on two-dimensional arrays. There is another version of this result corresponding to symmetric arrays. Okay, so namely, a symmetric array is called weakly exchangeable if the permutation of rows and columns by the same one-to-one function pi gives an array with the same distribution as the array S. Okay, for any one-to-one function pi. Okay, in this case, we have to preserve the symmetry of the array, so we have to apply the same permutation to rows and columns. And then, similarly to the above, one can easily imagine an example of such an array given in terms of functions of IID uniform random variables. Okay, so namely, you can take the array generated by a function sigma, where there is some randomness corresponding to the whole array, there is some randomness corresponding to rows and columns, except here this should be the same sequence, and this function should be symmetric in these two variables. And finally, you can have a dependence on random variables that depend on both L and L prime, but again, because of the symmetry, this should be a function that depends only on this set of indices L and L prime, so it should not depend on the order. Okay, where again, all these are IID uniform on 0, 1. Now, for diagonal elements when L is equal to L prime, here we can see that there is a dependence only on one index. So sometimes one takes another function, let's say g, that depends on omega and ul. So here you don't really need another source of randomness x, because ul and xll, they depend on the same index anyway. Okay, and then again, the Aldous-Hoover representation in this case states that all weakly exchangeable arrays are of this form in distribution. Now in the notes I give two very different proofs of these results, although one of them can be adapted to both, and in fact one of the exercises is to prove this first representation by the same method as the second one. And because the proof of the second representation in the notes is very similar to the proof of Definity's theorem in the last section, I'm not going to go over it here and just focus on a very different proof for the first representation. So here from now on we will focus on the first representation for exchangeable arrays. And the main step in the proof will be the following consequence of the Definity theorem. Namely, we will start by considering an exchangeable sequence of pairs. So the sequence will consist of two coordinates TL and SL, and if we permute this by any one-to-one function, we get equality in distribution. And our goal here will be to describe the distribution of the second coordinate conditionally on the sequence given by the first coordinate. Okay, in fact, for convenience of notation, let's denote this entire sequence by S and this sequence by T. And then let's consider an empirical measure of this sequence. So namely, let mu be the limit of empirical measures of these pairs T, I, Si. By Definity's theorem, we know that this limit exists almost surely, and in fact, conditionally on this measure, the sequence is IID from this measure. Now, we will also need the first marginal of this measure, let's call it mu1, so this will be a limit of empirical distributions of the first coordinate. Of course, this mu1 will be just the marginal of the measure mu on the coordinate of t. And a key step in the proof of Aldous-Hoover representation will be the following lemma, okay, which states that conditionally on the sequence t, the sequence SL of the second coordinates is equal in distribution to some function f of this empirical measure mu1, TL, and then new random variables here will be v and xl, where v and xl for L greater or equal than 1 are all IID uniform random variables, and the function f is a measurable function of its coordinate on the corresponding spaces where they are defined, with values in the space where this random variable SL belong. Here I don't specify what all these spaces are, but of course, as usual, we assume that we deal only with nice Borel spaces or even complete and separable metric spaces. Okay, so just for certainty, let's say that T's take values in space omega 1 and S's take values in the space omega 2, okay, which are complete and separable metric spaces. And notice here that since we describe this conditional distribution, the first two arguments are fixed. So mu1 is a measurable function of the sequence Ti. And what this representation says that this sequence SL, it will depend on this whole sequence T through the empirical measure mu1, and then each SL will depend only on the corresponding TL, and there will be two new sources of randomness. One will be common randomness for the whole sequence, and one will be individual for each index given by this XL. Okay, so now we will prove this lemma. To prove this lemma, let's consider this product space with one coordinate reserved for the sequence T, one coordinate reserved for the sequence S, and one coordinate reserved for the empirical measure of the sequence T, and one coordinate reserved for this empirical measure mu of the sequence TLSL. And first, let's observe various relationships between these coordinates. Now, first of all, let's notice that mu1 is a function of T. It's a measurable function of T because it's just an empirical measure defined in terms of the sequence T. Now let us also notice that mu1 is a function of mu, because mu1 was just the first marginal of mu, so it's a projection of mu on the first coordinate. Now, of course, mu is similarly a function of two sequences T and S, right? Because it was an empirical measure of the vectors Ts. Now, let's recall also that by de Finiti's theorem, we know that a sequence TL is IID from this measure mu1 conditionally on the measure mu1. So in other words, given mu1. And de Finiti's theorem applied to the pairs says that conditionally on the empirical measure, a sequence is IID from that measure. And first we'll begin by using this last statement, right, that the sequence of pairs is IID from this measure mu given mu. And first, given the measure mu and the sequence TL, okay, we will try to describe the distribution of the sequence SL. So our ultimate goal is to describe the distribution of sequence S given only the sequence T. But in the first step, we will also include the measure mu in the condition. Okay, so in other words, we are trying to understand the conditional distribution of the sequence S given these two random objects, mu and the sequence T. So our goal here is to describe the distribution of the sequence SL conditionally on both mu and TL. Now first, I want to say that this is actually a product measure. So given mu and the sequence T, all SLs are independent. So we can write this as a product over L of the distributions of individual coordinates SL given mu and the sequence TL. Okay, and this of course follows from the last claim above, because we know that given mu, all SLs are independent. Okay, to emphasize this a little bit more, let's say we were computing a distribution of S1 conditionally on mu, the sequence T, and the sequence S, except for this first coordinate 1, so for L not equal to 1. Then the above property that given mu, these pairs TL, SL are independent over L, right, means that in this condition you can erase all the other S's. And moreover, you can also replace this sequence TL by just T1. Again, because given mu, S1 is independent of T2, T3, and so on. So in particular, if we continue here, we can write the above product measure now as conditional distributions of each coordinate given mu and only the corresponding t with the same index L. And finally, when we recall that this sequence SLTL given mu has actually distribution mu, this is just a conditional distribution of the first coordinate given the second coordinate under this measure mu. As a result, given mu and given this sequence t, we can encode the conditional distribution of this sequence SL by some function h that depends on this empirical measure mu. For each SL, it depends on the coordinate TL, and then you can use independent uniform random variables XL to encode this fact that the coordinates SL are independent given mu and the sequence t, and the distribution of each SL depends only on mu and the corresponding t. And in fact, it's the same conditional distribution above, so we can use the same function h here. And so this describes a distribution of the sequence S given the sequence t and the empirical measure mu. And we want to get rid of this empirical measure mu. So in step 2, what we need to describe now is the distribution of mu given t. Okay, and here we are going to use various other relationships that we noted above. Okay, so first we know that the distribution of the sequence t given mu, right, so conditionally on mu our pairs were IID, and in particular this t was from the first marginal, which was just the empirical measure mu1 of this sequence t. But then let's note two things. So first of all, on the right hand side, of course, this is also the distribution of the sequence t conditionally on just its empirical measure mu1. So we didn't need to give any reference to the second coordinate here. But on the other hand, on this left hand side, we can add in the condition the empirical measure mu1. This is simply because mu1 is a measurable function of mu. It doesn't add any information. So the sigma algebra generated by the pair is the same as the sigma algebra generated by mu. And so we see we have this equality between these two conditional distributions here. And in particular, what this tells us is that given mu1, t and mu are independent. And then we can use this conditional independence as follows. So our goal above is to describe distribution of mu conditionally on the sequence t. And first thing, we recall here that in the condition we can also include measure mu1, because measure mu1 is just a measurable function of the sequence t, because it's just its empirical distribution. But we know that given mu1, t and mu are independent. So on this right hand side, we can now erase t in the condition. And so what this tells us is that conditional distribution of mu given t depends on the sequence t only through the measure mu1. So if you want to describe the joint distribution of t and mu, when you take conditional distribution of mu given t, it depends only on t through mu1, so you can encode it by some function of mu1 and some uniform random variable v on 0, 1. Right? In the general case, this function g should depend on t, but we just showed that this conditional distribution depends on t only through mu1, so we can represent it in this form. Okay, and now if we just combine 1 and 2 together, so in the first step we describe conditional distribution of this sequence SL given the sequence t and the measure mu, but now we describe conditional distribution of mu given t, so we can conclude that given the sequence t, the distribution of the sequence S coincides with the distribution of some function of mu, which now it can be encoded as g mu1 v, and then TL XL, where random variables v and XL are IID uniform on 0, 1. And of course, in this representation, you can write composition of two functions as one function of mu1, TL, v, and XL. Okay, and that was exactly the statement of this lemma, that conditional distribution of the sequence S given t can be encoded in this form. Okay, and now given this lemma, we will prove the Aldous-Hoover representation for exchangeable arrays. So here, for convenience of notation, we will consider this array SLL prime with the indices L as before, so greater or equal than 1, but we'll take the second index L prime to be all integers, because in the proof we will be conditioning on half of the array, so it will be convenient to take half for L prime less than or equal than 0. And so given the array here in this picture, what we have is that the columns represent the array SLL prime for all L for a fixed L prime. And half of the array for L prime less than or equal than 0 is given by this green box here. And finally, we will also need to use these YLs given by these rows. It will be half of the row only for L prime less than or equal than 0. And first, we'll just take a look at the columns. So if we consider the sequence of the columns XL prime, by exchangeability of the array, of course, this sequence will be exchangeable as a sequence. And in particular, we can apply Definiti's theorem to this sequence. And in particular, in Definiti's theorem, we showed that conditionally on half of the sequence, another half is IID. So conditionally on that green box, which I call X, so all X L prime for L prime less than or equal than 0, the columns XL prime are IID, okay, for the other half, for L prime greater or equal than 1. And so as a result, our goal will be to describe the distribution of just one of them, x1 given x. Okay, because once we know this conditional distribution, all the rest are IID with this distribution. And so on the right hand side of this array, we now just take a look at the first column x1. And we want to understand the joint distribution of this one column given this green left half of the array. And so now we will view this left half of the array as actually a sequence of rows. So this will be a sequence YL for L greater or equal than 1. And also our first column x1 on the right, now we'll also take a look at this as a sequence SL1 for L greater or equal than 1. So now we bring back the index of the rows. And of course, the exchangeability of the array implies that if we look at these pairs, YL, SL1 for L greater or equal than 1, this is an exchangeable sequence. And this is where we are going to use the previous lemma. So by previous lemma, if we denote by mu here the empirical measure of the sequence Y, now recall in the previous lemma it was denoted mu1, but here I will just denote it by mu. And then the previous lemma states that conditionally on the first sequence or sequence of the first coordinates, the sequence of the second coordinate SL1 can be generated by some function that depends on our sequence Y only through its empirical measure, and then each coordinate L depends on Y only through YL otherwise, and then we have some independent sources of randomness V, which I will denote V1 here, and XL, which I will also denote XL1, okay, for L greater or equal than 1. Okay, where, as usual, these two were IID uniform on 0, 1. So the reason I included that index 1 here to emphasize that conditionally on Y, or the sequence Y, which actually is the entire half of the array, the only sources of randomness here is this V and X. And that is what describes the distribution of the first column on the right. So the index 1 here corresponds to that index 1 on the right hand side. And since in the first half of the proof we said that conditionally on this left half of the array the columns on the right are IID, and we describe distribution of one of them, now we can conclude that the distribution of SL L prime for L greater or equal than 1, and also L prime is now going to be on the right, so greater or equal than 1. Okay, we just have to plug in independent copies of these random variables V and X for different indices L prime. So we get the representation of this form. And now we are getting very close. So finally, we just have to recall that this sequence YL is IID from its empirical measure mu. And so just like before, we can encode this measure mu by some function of some random variable W, and then we can encode the sequence YL by some function of its empirical measure and some independent IID uniform sources UL. And if we combine this with the above, we get that our array SLL prime for L and L prime greater or equal than 1 is equal in distribution to some function of W, UL, VL prime, and XLL prime. Okay, where all these arguments are uniform IID on 0, 1. Okay, and so this finishes the proof of this Aldous-Hoover representation for exchangeable arrays. We will give some further examples of these types of results in the exercises, and in the next section we will give one example of application of this Aldous-Hoover representation that we just proved to the so-called Gram-Definetti arrays.